Okay, I forgot to lecture about one little detail in this module, and that is energy diagrams. So there are lots of important things you can learn from these energy diagrams. So I've drawn two here. As you can see on the y-axis you have energy, low energy to high energy. On the x-axis, just the reaction progressing, like the reaction starts here and it just keeps going until its end point. There are two diagrams here, somewhat different. Hopefully they're starting right about the same energy. Hopefully this is also about the same energy, just so we can compare them. So let's look at what they mean and what the differences between these two reactions would be. So here we start at a given energy, and then every reaction has to go up over this little hump. Now this is called activation energy. It starts at the energy where all of the reactants begin, and it goes up to the peak, the highest energy point here. So I always denote it as A sub E, activation energy. Some people just call it a big capital E for energy. Activation energy is the energy required to get a reaction going. Next week I will do a reaction with ammonium dichromate for you as a demonstration outside. And so you'll see that it requires me to put in a little bit of energy to get the reaction going. Once I get it going, it will produce enough energy to sustain itself and keep going. But you always have to get a reaction started and add a little bit of energy to get it going. And that's the activation energy. Now, the amount of energy required could change. Like, I could lower the activation energy by using something called a catalyst. So, for example, if I had a similar graph like this, and it had an activation energy and then it ran, well, I guess it would be similar to this one. If I decided to use a catalyst, I could add the catalyst to the reaction. It would lower that activation energy. And there are two kinds of catalysts that you'll learn about in, I think, this module, so I'll just talk about them. So you could have a heterogeneous catalyst, and you could have a homogeneous catalyst. Okay, so a homogeneous catalyst has to be the same phase as one or more of your reactants. Same phase. So let's say I had two liquids reacting together. If my catalyst were a liquid, it could be homogeneous. A heterogeneous catalyst would be a different phase than any of the reactants. And I'll do a demonstration of that at some point too, where we'll see some catalysts that work. They just lower that activation energy so that it requires less energy. It will speed up the reaction rate. Actually, this is going to be like in module 15, I bet, because it's reaction rate. But a heterogeneous catalyst will be a different phase, and they have different reaction mechanisms, which I was about to talk about, but I'm not going to because I'm pretty sure it's the wrong module. Anyhow, but you'll see that later. So, ignoring activation energy changes because of catalysts, you can see that the activation energy in this diagram and in this diagram is about the same. It goes from here to about here. Assuming that the two axes are the same, the activation energy would be about the same. If you wanted to have a smaller activation energy, you would just see a smaller hump. It would go up less, for example. It would take less energy. So I would say this reaction has a larger activation energy than this reaction now that I've changed it to be a smaller hump. So, and you could, even if I had measured off the y-axis, you could say this was 100 joules and this was 200 joules or something similar. So activation energy is just the size of the hump from where you start to the tippy top. It's the amount of energy required to get the reaction going. So once you get over the top of that little hill, you have that reaction going, and it will go until the reaction is finished at equilibrium, which you'll learn about later too. So, if you end up with a higher energy state for your products than you started with for your reactants, so I could go over here and say I started at this energy level, which if that were a straight line, that would be really good. Try that again. Straight line. And then I increased in energy. My products have more energy than my reactants did. Then I see that I've gained energy. So this would be an endothermic reaction. Right? An endothermic reaction. It has gained energy. It has absorbed energy from its surroundings. Endothermic. Has more energy at the end than it did at the beginning. Right? So delta H, the change in enthalpy, change in energy, for example, would be positive, right? It has gained energy from here to here. Similarly, if I drew a line across here and I said, well, my products are at a lower energy state than my reactants. I've lost energy through the course of this reaction to the surroundings. Then delta H would be negative. Energy has been lost from the beginning of the reaction to the end, from the reactants to the products. So this would be an exothermic reaction. It has given off energy. You know that fire is exothermic. Next week we'll do an acid-base reaction and a calorimeter that's exothermic, so you can see how this works, measure it, and do the math for delta H for that. So this reaction will be exothermic. It started at a higher energy state, it lost energy to its surroundings, gave off heat like a fire, and that's exothermic. So energy diagrams can tell you lots of information. How much activation energy is required to get the reaction going, if the thing is endothermic or exothermic, and, well, actually a few other things also, but that's really all you need to know for Module 13, I think. So, you have a few questions about that. Let's see. Maybe I will take a quick look at the review questions and see if there's any more. I don't think so. I'll stop this video there, and this time I really will talk about combustion and methane on the next video.